So we're going to be continuing. If you were with us the last time, we gave an introduction to this topic of creation and evolution, worldviews, and conflict. So we want to briefly go back and touch on a few of the points we looked at. So again, what is a worldview? The overall perspective from which one sees and interprets the world, a collection of beliefs about life and the universe held by an individual or a group. All people have a worldview, and there's a lot of different worldviews. Our focus here is going to be on worldviews as it relates to origins. But again, all people have a worldview, and they just naturally interpret evidence based on the worldview that they have. You know, if you watch the news or read the newspaper or have a conversation with a neighbor, you're actually bringing your worldview to that point. And I illustrate it again. It's like having glasses. I'm looking through my glasses. I don't normally think about it, but I see the world that way. And that's what a worldview is. We have the same facts on this planet, but do facts speak for themselves? A couple of weeks ago, I was summoned for jury duty. You know, why do we have a courtroom? Why do we have juries, judges, prosecutors, defense attorneys, if facts speak for themselves? The reality is facts have to be interpreted and put in a framework and understood. And again, if you have a prosecutor and a defense attorney, they're going to try to get you to look at the facts from different perspectives. So again, we do have the same facts, but we often see them, interpret them differently. We have the same science, obviously. Science is practiced all over the earth today. Doesn't matter what background you have, you can practice science. And again, what is science? This is an Oxford Dictionary definition. The intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. So we all have our mental image of somebody wearing a white coat, being in a laboratory, conducting experiments. And you can wear that white coat, again, in Brazil, in Russia, in China, in America, it doesn't matter. And you conduct the same experiments and follow the scientific method. But when it comes to origins, we need to think about science in a little bit different way. There is what we can sometimes refer to as operational science, which is simply what we would normally call science. It operates in the present, utilizing the scientific method. When you're talking about origins, you're now looking at what could be called origins, historical, or forensic science. And in this case, what you're doing, of course, is observing the present, and based on the evidence that you see in the present, you're seeking to understand what actually happened in the past. And that always involves looking at facts and applying your worldview and interpreting what you see. We talked about what is a religion, and religion, two different definitions here. A set of beliefs concerning the cause, nature, and purpose of the universe. And here, if we're talking about creation, obviously it talks about the cause, the nature, and the purpose of the universe. But if you actually talk about naturalism, materialism, Darwinian evolution, likewise, they have a view about the cause, nature, and purpose of the universe. And also the definition, something a person believes and follows devotedly, a cause, principle, or system of beliefs held to with ardor and faith. And I think you can recognize that a strong Darwinian evolutionist has this strong ardor belief system. Naturalism is not science, does not meet the definition of science. It does meet the definition of religion. And again, as I said, sadly, many of our courts have been convinced that naturalism is science, and therefore it is taught in a lot of school systems and promoted by Hollywood and other venues. So we're going to be looking at some challenges to Darwinian evolution. And teleology is what we're going to focus on tonight. And that's the appearance of purpose and design in the universe. We'll expound on that. In coming sessions, we'll be looking at other things, and all of these, I believe, present significant challenges to the Darwinian model. So we'll be taking a look at all of these in the future. Now, teleology. Teleology was once widely taught in universities. This may come as a surprise to you, where now Darwinism is intertwined into most universities, and some people take an official course in Darwinian evolution, but it's clearly ingrained in the social sciences. William Paley wrote several highly influential books on philosophy and Christianity. Two of those are listed here, Evidence of Christianity. This was required reading at Cambridge University for over 100 years. His most influential book was Natural Theology. And of note, when Charles Darwin attended Cambridge, he studied the writings of Paley, and it was actually a part of his final exam. He actually said that these were amongst his favorite areas of study when he was at Cambridge. I mean, he liked natural sciences and the logic and approach that Paley took in taking natural world and using that as an apologetic or defense. Actually, at that point, Charles Darwin said he thought it was very intriguing and he studied it diligently. There's two competing worldviews, again, concerning the earth, and I want to present both of those here. One is the earth is not specially favored. This is the materialistic worldview. The other is that the earth is specially favored. This is the creation worldview. The materialistic view is codified in what's called the Copernican principle. Now, I think it's a bit unfortunate that they used Nicholas Copernicus to define this principle. He himself was a devout believer. He was a Roman Catholic priest, and he clearly believed in the God of the Bible. But if you recall your history, it was Nicholas Copernicus who, around 1500-ish, put forward a modern interpretation of the planets and the earth are going around the sun in orbit. That's called the heliocentric model. Prior to then, the geocentric model was widely believed. It goes back to ancient times. The Greeks and Aristotle believed that. The Romans believed it. The Chinese believed it. And even through time, the Christian church adopted that because that was the prevailing scientific view of the age. The Bible itself doesn't talk about this. The Bible does say that the earth is a sphere hung upon nothing, but it doesn't talk about whether it's traversing the sun or whether the sun is traversing the earth. That's not in the Bible. But it also shows the danger of the church simply accepting current science because, again, the geocentric model was held for at least a couple of thousand years. Michael Rowan Robinson, who is actually a British astrologer and astrophysicist, he's a professor at Imperial College. He was the former president of the British Astronomical Society. He clarifies and states what is the Copernican principle. He says, it is evident that in the post-Copernican era of human history, no well-informed and rational person can imagine that the earth occupies a unique position in the universe. Now, the last time we talked about another statement, we hold these truths to be self-evident. And when the writers of the Declaration of Independence and those who signed it, they were expressing a worldview when they stated that. Well, clearly, Michael Rowan Robinson is expressing a materialistic worldview, saying the earth, again, does not occupy any unique or special position in the universe. Now, I may bust a little bit of a bubble here, but if you're a fan of science fiction, and I enjoy a number of those movies, they clearly have bought into this worldview. The idea with Star Trek and Star Wars and Guardians of the Galaxy and all of these movies is that the universe is teeming with life forms, right? And the earth is simply one of the thousands or millions. And that view is held by many people, including those at NASA. We spend, as you might expect, millions of dollars a year as a government, and over time, billions exploring space, looking for intelligence. And so this is the materialistic worldview, that the earth is really not special. And there are bound to be many places just like Earth throughout the galaxy and throughout the universe where life has emerged. That's that worldview. Well, clearly the scriptures present a different perspective on the earth. For thus says the Lord, who created the heavens, he is God, who formed the earth and made it, he established it. He did not create it empty, he formed it to be inhabited. I am the Lord, and there is no other. So the scriptures declare by God himself, this is a direct quote, I formed the earth to be inhabited. So it is unique, and it's very special. So two different views, not special and special. So now you're the jury, and we're going to take a look at some of the uniqueness about the planet Earth, okay? And then you can make your own decision. Another passage that's relevant for what we're going to be looking at tonight, Psalm 19, you're all familiar. The heavens tell of the glory of God. The skies display his marvelous craftsmanship. Day after day they continue to speak. Night after night they make him known. They speak without a sound or a word. Their voice is silent in the skies, yet their message has gone out to all the earth, their words to all the world. Again, if you've gotten to a dark place, and I think most all of you have, you look up at the heavens on a clear night and you're awestruck, right? There's no language spoken, yet nevertheless the heavens are speaking to you about the glory of God. That's what the scripture's telling us. Let's think about the planet Earth. Okay, we're going to look at some unique factors. To start with, you may not have thought about this, but our solar system is located in what's called the galactic habitable zone. Now, what is that? Well, as you can see in the first picture up there, our solar system is located between the Sagittarius and Perseus arms of the Milky Way. Most places inside of a galaxy are not suitable for life. If you were to go into either the middle of the galaxy or into the middle of the spiral arms, the radiant intensity is so severe, and the collisions that take place happen so frequently that it's not conducive for life. And when you get a lot of stars in close proximity, they also get into kind of a gravity lock. You have dual stars, and you have groups of stars that are locked. That's a bad place for planets to be, when there's multiple stars are in gravitational lock. So again, the estimate is that, and this comes from astrophysicists, astrobiologists, less than 3% of all stars are in what's considered the galactic habitable zone. Well, what about our star, Sun? Our star is a main sequence G2 dwarf star. Did you know that? It has a suitable radiant spectrum and size to support planetary life. So our sun, to start with, is the right color. It emits a lot of visible light. Visible light is what enables photosynthesis to happen. The most common star found in the galaxy or the universe is the dwarf red star. It predominantly emits long-wave radiation, which is not suitable for life. Our star is also considered quite stable. Many other stars actually produce a lot more flares, and they have a lot more solar activity that's harmful for life. And it's also the right size in terms of the habitable zone that exists around the star, which we'll talk about more. So the current estimate, again, by astrobiologists and astrophysicists, is that less than 5% of all stars are considered habitable stars. So again, less than 3% of the places in a galaxy, now less than 5% of all stars. The Earth is located within the solar system's habitable zone. And by that, we're talking about the distance from the sun to where liquid water is possible on the surface of the planet. Consider this. If the Earth was 5% closer to the sun, then our oceans would evaporate. If the Earth were 20% further from the sun, the oceans would freeze. Now, if you do the math on that, it turns out that only 0.01%, 1 part in 10,000 of the entire solar system is in a place where liquid water on the surface of a planet is possible. And guess what? That's where we are. only 1 part in 10,000. Okay? Now, beyond that, if the Earth traveled much faster in its planetary journey around the sun, its orbit would become larger. If it moved slightly slower in its orbit, then we would move closer to the sun. The Earth's trip around the sun is consistent to within a thousandth of a second. 365 days, 6 hours, 49 minutes, 9.54 seconds is how long the Earth takes to go around the sun. And we stay in the habitable zone. Now, from the Royal Astronomical Society, just one memo, astronomers now know of around 4,000 planets that orbit around other stars. A handful of these are both Earth-sized and in the habitable zones of the stars they orbit, where the temperature is right for liquid water. But many candidate Earth-sized worlds are in orbit around red dwarf stars, much smaller and cooler than our own. To be in the habitable zone, the planets need to be much closer to these stars than we are to the sun. The problem, however, is that red dwarfs can produce significant X-ray emissions and often have large flares of radiation and eruptions of particles in so-called coronal mass ejections. It goes on to say that planets around the commonest low-mass stars are not great places for life, and they go on to say that talk of an Earth 2.0 may be premature. But here's another interesting thing about the Earth. There's something called orbital eccentricity. This has to do with how perfectly circle is an orbit. So if a planet or any object like a comet was in a perfect circle, meaning the exact same distance from the sun all the time, its orbital eccentricity would be 0. Okay? Our planet, again, slightly shifts, from basically 92 to 94 million miles away from the sun. And we have an orbital eccentricity of 0.017. If our orbital eccentricity was as much as 0.04, we would be going inside and outside of the habitable zone over the course of the year. So if we followed a more elliptical orbit than we do, if we were as much as Jupiter, Saturn, Mars, Mercury, Pluto, part of the time during the year we would be outside the habitable zone. So our planet is in that 1/10,000th part of the solar system where liquid water is possible, and it always stays in that zone continuously. The Earth is a terrestrial planet, a metallic core, silicate mantle, rocky surface. It's not one of the gas giants, obviously. It has an abundance of carbon, oxygen, and all the other elements essential to support complex life. The major elements, you can see there, they can be thought of as by an acronym, chin-ups. So carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. 97% of your body is made up of those 6 elements. However, life, particularly complex life, like our life, we have other elements. You're very familiar with iron and the blood, or iodine and the thyroid, but there are many other elements. Our planet has all of those elements on its surface, and it turns out that that's rare. It's unusual to find all of the elements present in one location. Another article. Amid efforts to find alien life, scientists have not yet confirmed the existence of an extraterrestrial civilization. Findings of a new study suggest that this has something to do with the element phosphorus, which is lacking in the cosmos. Phosphorus is the 11th most common element on Earth. It's fundamental to all living things. Phosphorus is one of the 6 primary chemical elements on our planet that organisms depend on. And this will make sense to you. Phosphorus helps form the backbone of the long chains of nucleotides that create RNA and DNA. Now, we'll be talking more about that at a future session. But if you remember, DNA is like a ladder. The backbones, or the ladder rungs, are made up of sugar, phosphate, sugar, phosphate, sugar, phosphate. If you didn't have phosphate, you wouldn't have DNA. You wouldn't have RNA. Okay? That's the first thing it's talking about. Also, phosphorus is found in our cell membranes. Phospholipids are in all of our cell membranes. And then beyond that, you have the power-generating part of every cell called ATP, adenosine triphosphate. Again, these critical components in living organisms all depend upon phosphorus. Astronomers have been hunting for phosphorus in the universe because of the role it plays in life on Earth. If the element is lacking in other parts of the cosmos, it could be difficult for alien life to exist. A new study presented at the European Week of Astronomy and Space Science meeting now suggests life as we know it is more unusual than previously thought because the universe substantially lacks phosphorus. So when they study stars and they can look at spectrums and they can look for elements, they're finding that phosphorus is highly unusual, and yet we have an abundance of it on our planet, along with all the other elements needed to support life. The Earth is the right mass with a suitable gravity to support complex life. Gravity impacts the surface terrain of the planet, the amount of atmosphere, the cloud cover, rainfall, surface temperatures, and other such things. So just a few comments on the right size. If the Earth's diameter was 20% less, its mass would only be half of its present value, and most of the atmospheric gases would then escape into space. So if it was a little bit smaller, we would lose an atmosphere. If the diameter was 20% greater, the gravity forces would be 25% larger. That would place a greater strain on living organisms, particularly our joints, our skeletons. But it affects other things too. The higher gravity would actually cause the surface of the Earth to be smoother than it is. The Earth is actually remarkably smooth. If you can imagine reducing the size of the Earth to a 1 meter ball, then the highest peak above that ball would be 1 millimeter, 1,000th of the diameter of the Earth, and the deepest trench would be 1 millimeter. Okay? And it so happens that if the Earth was completely smooth, and if the gravity was larger, it would force the mountains to be smaller. If the Earth was completely smooth, the entire Earth would be about 2 miles underwater. If you redistributed all the water equally, we would be inundated completely with water. So, again, we have the right mass. This is something, again, people typically would not think about, but the Earth is actually protected by the large outer planets whose gravity helps sweep the solar system. Now, on that previous slide, you saw that Jupiter is about 318 times larger than the Earth, and Saturn is 95% times larger. Well, all of those outer planets that happen to be much more massive than the Earth, they suck up meteors and asteroids and things that otherwise could impact the Earth. And so we are actually being protected by these large outer planets. The Earth has a strong magnetic field, or magnetosphere, that protects living organisms from damaging cosmic rays and solar winds. So here, consider all the terrestrial planets. Earth, if you look at our relative strength of magnetic field as 1, look at the other terrestrial planets. Essentially, they have no magnetosphere. That means that those planets are being inundated continually by cosmic rays, by solar winds. The surfaces are being just flooded with particles that are harmful to life. We also, as you know, have an ozone layer. Now, this ozone layer is well above the surface of the Earth. It's like 6 miles up to 30 miles above us. And what the ozone does, it absorbs essentially 100% of the UVC, which is the most harmful UV that comes from the sun. Again, almost 100% absorbed. It absorbs most of the UVB, which is the next most harmful, and then it blocks some of the UVA. So we're all concerned, particularly here, about our exposure to UV. Well, the ozone layer is doing most of the protection. So if we did not have ozone, we would be getting bombarded with UV light that would basically kill off life. If you remember back in your school days long ago, they talked about an Earth in its primitive state not having oxygen. And here's an interesting thing about that, a paradox. It's commonly held that the primitive Earth did not have oxygen in its atmosphere. Otherwise, amino acids would not form. However, if there was not oxygen, there would not have been an ozone layer, and the ultraviolet radiation would destroy any amino acids that did form. So that's a paradox. And in reality, there is no evidence that the Earth was ever without an oxygen atmosphere. The rocks, as you dig down in them, they all indicate that there's been oxygen in our atmosphere. An interesting thing about this, the Earth's rotation, 24 hours, right? This evenly distributes the sun's energy, promoting temperature uniformity and distributing sunlight to support complex life. Now, if our planet was like Mercury, it would take 59 days to make a revolution. If we were like Jupiter, on the other hand, it'd be spinning in 10 hours. That's really fast. Well, this has some impacts on us. So if the Earth's rotation on its axis was much slower, the temperature differences between day and night would be extreme. During the day, temperatures would become intolerably high, and the extended influx of sunlight would dry out the surface. During the long night, it would become exceedingly cold. So slower is not good. However, if the Earth rotated much faster, then temperature differences between day and night would decrease. This would negatively impact weather patterns, and also the increased centrifugal force would cause a greater loss of atmospheric gases. So we seem to be turning at an optimum rate to promote life. Furthermore, the length of the year, 365 days, is optimum for plant life cycles. So we're coming out of summer, but we've just had a growing season in the northern hemisphere. And broadly speaking, May, June, July, August is our growing season, right? So the year of 365 days gives the northern hemisphere and the southern hemisphere each ample time to have a growing season. Okay, so that 365 is actually very beneficial. For comparison, one Uranus year is 84 Earth years. That's how long it would take. That would mess things up if it took 84 years to go around the sun. Now, here's another one that I find quite interesting. We have a large moon. That's obvious, right? There's about 290 moons in the known solar system. Most of those are around the larger gas giants. But one thing that the moon does, it allows the Earth's tilt to be stationary. Our Earth is tilted 23.4 degrees on its axis. Now, again, this is what gives us the seasons. So during part of the year, the northern hemisphere is tilted towards the sun, right? So therefore, we have summer. And then part of the year, the northern hemisphere is tilted away from the sun, and we have winter. That's, again, 23.4. Well, the moon, basically, its gravity fixes the tilt of the Earth. They've modeled what would happen if we did not have a moon. And the tilt would be varying between 13 and 33 degrees. The Earth would be wobbling if we did not have that. So having a moon is very important. Now, it does other things too. Obviously, it creates tides and it mixes nutrients. It has other benefits for us. But here's, if you think about this, that 23-degree tilt, well, we could be like Uranus and be tilted 98 degrees, or essentially part of the planet facing the sun continuously, and part of it facing away from the sun continuously. If that happened, then the part facing the sun, again, would be exceedingly hot, and it would be dried out. And the rear part would be exceedingly cold, and in between, you would have an extremely dynamic weather pattern. Super hot air, super cold air, hitting each other, and it would be very destructive, and life would not be possible if we were tilted like Uranus. Now, if we were like Mercury, which has virtually zero tilt, at first thought you might think, well, that sounds pretty good, That's basically like a spring equinox or a fall equinox. We're approaching that right now. But it actually presents a problem. If you think about our country, the United States, the last time that we typically experience a freeze, if you go down to Atlanta and all the way to Dallas, that's in mid-March. And occasionally, those places experience a freeze into April. Well, if you went further north in America and into Canada, you would have freezing every day of the year. So what kind of a growing season would you have if every night it froze? You know, how good would your corn do? How good would your soybeans? How good would your tomatoes do? So basically, the fact that we have this 23-degree tilt enables the seasons, and it increases the habitable area of the entire planet. Without that, the northern part, the southern part, would largely be uninhabitable. So it turns out people that have done calculations have determined that 23 degrees appears to be the optimum tilt for a planet. Another just side bit. We're unusual in that even though there's 290 moons found throughout the solar system, there is only one place in the entire solar system where a perfect solar eclipse takes place. Where's that? The surface of the earth. It's the only place. They've modeled the moons, they've modeled the planets. And why is it that we can experience a perfect solar eclipse? The moon is 1/400th of the diameter of the sun, and the sun is 400 times further away than is the moon. Therefore, the moon and the sun have the appearance of being the same size in the heaven. Now, the fact that the moon occasionally passes in front of the sun has enabled scientists to actually study the corona and learn and understand how stars function. And it's also given modern-day scientists the ability to demonstrate that gravity actually affects light rays. It bends light. They've been able to study stars as they went behind and seeing how actually we could see stars that were literally behind the sun because the light rays were passing and bending. So it also appears that the earth is a perfect place for observation. Where we're located allows us to look into the universe and understand it. It allows us things like to see how the sun operates. So I think that's quite amazing. The earth has an atmospheric pressure and composition that is suitable for complex life. So you can take a look there at the relative atmospheric pressures of different planets. So consider Pluto, none. Mercury, none. Mars, 1/100th of the planet Earth. Some people occasionally say, if we keep messing up the earth, then I just want to go to Mars. Let's build a colony on Mars. There's no place on Earth that is nearly as bad as the surface of Mars. Not only do you not have an atmosphere, not only is it much colder, but you're being continuously bombarded by cosmic rays and solar rays. It's an undesirable place to be. We are living in the right place, okay? So our atmospheric pressure works very well for life, and the composition of our atmosphere is also very suitable. You can see the other planets. We're very unique in having roughly, you can see 78% nitrogen, 21% oxygen. If oxygen happened to be as high as 50%, we would experience what's called oxygen poisoning. If it were as low as 10%, you couldn't start a fire, okay? So it appears that we have the right amount. Nitrogen also absorbs some of the radiation that comes into the earth. It, of course, helps us create the 1 atmospheric pressure. It contributes to partial pressure to the atmosphere. So here, again, we have what appears to be the optimum atmosphere for life, and it's highly improbable and highly unusual. Another thing about the earth, again, in the oceans, over 70% of the earth is oceans. And oceans serve as heat sinks, and they help to distribute the temperatures around the planet. So actually, they are helping to, if you will, buffer the atmospheric temperature. So we have a suitable, actually a desirable ratio of water to land mass in order to have a more balanced temperature profile. And of course, an interesting thing here again, if you had just 10% more surface water than we have today, 10% more surface water, sea levels would rise 2,900 feet above where they are today. Now think about the United States. If the only land that was exposed is above 2,900 feet, you would have some of the Rocky Mountains and a little bit of the Appalachian Mountains, but the vast majority of our surface would be underwater. And of course, that's true of the rest of the planet as well. Just 10% more. We have what appears to be the right amount of water on the surface of our planet. If you had substantially less water, the land masses would be greater, but you would suffer from not having the same kind of distribution of heat, and you would have vast arid areas. So like the Sahara Desert, much more of the land mass would actually be dried out. So it appears, again, that we have about the right amount of water for life. This one bonus comment here, there was a sea captain in America, Matthew Maury, who was reading the scriptures, and in Psalm 8:8 it says, whatever passes through the paths of the seas. And that intrigued him. And based on the idea that there are rivers in the oceans, paths in the seas, he set out to study the currents, and he prepared the first oceanography textbook in the world, just from reading scripture. Now we've got all of this water, but what if the water was not a pH of 8, which is essentially neutral? Hydrochloric acid is basically a pH of 0. Sodium hydroxide solution is basically a pH of 14. I didn't mention earlier, but on Venus, they have sulfuric acid clouds, okay? If we had sulfuric acid clouds here, we would have a very low pH in our oceans. We have the right pH that promotes life on our planet. And then one other factor, the temperature profile of water, of the atmosphere. This shows you the actual temperature. If you go up to about 33,000 feet, a lot of airplanes fly there, it's roughly negative 50 degrees centigrade all over the earth. It's hard to imagine, but actually you can go to the Arctic, Antarctic, or the equator, and the temperature at 35,000 is essentially the same everywhere. Well, the temperature profile actually works to trap water next to the surface of the earth. Water has that molecular weight of 18. You've got nitrogen 28, oxygen 32. Actually, water vapor is actually lighter than oxygen and nitrogen. It might tend to float up. But as it stands, because of the temperature profile of the atmosphere, the water is trapped against the surface of the earth. So, interesting. So, considering this, the earth, is it special or is it ordinary? You can be the judge. Each one of these factors that we've talked about, and there are others, are of themselves improbable. And the way you have to start thinking about this is you multiply the probabilities of all the factors to come up with how probable or improbable such a thing is. And we have a video to support that. So let's watch this together.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, but has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that has an atmosphere that has enough oxygen to to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
So again, what they're saying is if the Milky Way galaxy has 100 billion stars, which is the current estimate, some say it might be 300 billion, but it's to the order of 10 to the 11th. If you assume even that if most of those stars had planets, some people have then speculated, well then, since there's nothing special about the planet Earth in our solar system, there must indeed be life throughout the galaxy. However, when you consider all of the unique factors that must be present simultaneously to support complex life, those that have been mentioned here plus others, then a different picture does emerge. And that is, the Earth is remarkable and highly improbable. And again, not to bust your bubble, but as they said, if you took 100 billion stars, but then you took into consideration 20 factors that need to be present simultaneously, they said that's 1,000th of 1 trillionth, which means it's highly unlikely on probabilistic factors that there's even one Earth in the solar system, but there is one. And you can actually extend that to the whole universe and easily come up with a similar kind of determination that it's highly probable that the Earth is the only place in the entire universe with all of these factors present simultaneously. Now, again, I enjoy science fiction, but the reality is, instead of calling it science fiction, it would be better to call it non-science fiction. Because if you actually understand the science and you watch a lot of those shows, you actually see how often in the movies they violate laws of science. You know, beam me up, Scotty. To totally take your body down to atoms and transmit your atoms and reassemble you simultaneously, that's not science. And that's non-science. And the idea that you can go from stationary to warp speed instantly, well, our bodies can only stand so many Gs, and you would instantly be crushed and dead. It actually would take days to speed up to even a quarter of the speed of light for you not to die in the process. If you're in a spacecraft flying through and you hit a small particle traveling at like a quarter of the speed of light, it's the equivalent of like an atomic bomb going off, striking you. So those movies, which are fun, are non-science fiction, okay? So we're talking here about what we actually do know from science. Now, teleology is not limited to the Earth and astronomy. Now, again, the appearance of purpose and design. We're going to be watching one other video that takes a look at what physicists understand as the precise fundamental forces of the universe. They're amazed at how finely tuned our universe is. And it's so improbable that all of these forces are tuned as they are, this has led to what you now see in science fiction when they talk about the multiverse, the notion that there are multiple universes. Why did they come up with that? They looked at how improbable it is that a universe exists that has all of these fine-tuned factors present. And it's so improbable, these people that are speculating are saying there must be an infinite number of universes, and we just happen to have hit the jackpot and to be located in the one that has all of the factors where all these things take place. Again, that's not science, right? That's a worldview. That's a naturalistic worldview. But it's just them wrestling with the notion that it appears that the earth is special. It appears that our universe is special. So that's another area. We'll look at one thing. Human consciousness. If you think about that, is consciousness necessary for life? Well, there's grass out there that seems to be getting along okay. And there's other creatures out there that don't experience consciousness. Of course, the scriptures teach that we've been made in God's image. So there's something unique about us. Morality, as we saw the last time we met, a naturalist, a materialist really does not have a basis for morality. What they routinely do is steal from the Christian worldview, without admitting it. The idea of that you shall not commit murder, you shall not steal. If you took the pure survival of the fittest mentality, let's face it, the goal then is to reproduce as much as possible. But what does that lead to? Morality or immorality? It leads to immorality if you took it literally. Okay, so morality also points to there being something more. Beauty. This past week, Selby Gardens had issued, they had a photo contest of photos that people had submitted of pictures taken within the gardens. And if you happen to see that, go through it, it's like 100 beautiful pictures, and it's all focused on beauty, all kinds of artistic photographs that they've taken. Obviously, beauty is not essential for life, and yet there's beauty all around us. And laws of logic are another. All of these are examples of teleology, and we'll watch a video here and then look at one other example of teleology.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you're to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed, even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
This is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces are all important, the masses of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work. And not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible part I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
So, an amazing universe. The last thing I just wanted to talk about is what's called biomimicry or biomimetics. The definition here is the design and production of materials, structures, and systems that are modeled on biological entities and processes. Now, remember, the materialistic Darwinian view is that there is no such thing as design in nature. Okay? Why is that? Because design means, this is the definition in Webster's, to create, fashion, execute, or construct according to plan. Design involves having a plan. Darwinian evolution says that what's happening is random genetic mutations acted upon by nature result in survival of the fittest. And there is no goal. It's simply some random event happens and the organism somehow benefits. It's able to out-reproduce its peers. It's actually kind of a strange concept, really. But again, the materialist view is there is no such thing as design in nature. Yet, engineers, scientists have designed hundreds of products based on what they see in nature. Okay? So we're designing based on non-design. Few examples. Microbial film. The studying of the shark skin, it has denticles. And in studying those, Speedo actually designed a swimsuit that was used in the 2008 Olympics, and 98% of all the swimmers who won medals in 2008 was wearing the Speedo bathing suit. And as a result, because they determined they were getting an advantage over others, the Olympic Committee banned the use of that technology going forward. That what we learned from the shark skin is also applied to the hulls of some ships to make them resistant to microbes and barnacles and things like that. So that's one example. Japanese engineers who are famous for their design of the bullet trains, fast trains, were looking for opportunities to make them better. And they actually studied the kingfisher bird. And based on their study of the kingfisher bird, they redesigned the front part of these bullet trains. And now, using 10% less energy, they go 15% faster, and they've eliminated what's called tunnel boom. Again, they were simply looking at how the kingfisher dove into the water and created virtually no splash. And they studied that, applied engineering principles, and then improved their trains. Some types of whales, humpback whales, have these bumps on their fins. It kind of looks odd to us, but as it turns out, those bumps have been adapted to a number of windmills or solar panels, wind panels, and likewise, these can turn much slower and generate more electricity. They found it's much more efficient. So wind turbines have been redesigned with this feature. It enables them to generate the same amount of power at 10 miles per hour versus 17 miles per hour of wind using the traditional design. Again, based on the humpback whale. Termite mounds. People studied termite mounds and the ventilation that's present inside the termite mound, and they subsequently built this complex in Zimbabwe, and it uses 10% less electricity to cool versus the traditional design that they had used. And then the famous woodpecker. Woodpeckers bore holes. They experience a deceleration of 1,200 Gs, or gravitational pulls, approximately 20 times per second. By comparison, a severe car crash may deliver 120 Gs, that's 1/10, to a passenger in the car. So researchers have identified several unique design features that protect the woodpecker, including a semi-elastic beak, an area of spongy bone behind the skull, and cerebrospinal fluid that inhibits vibration. Using these design features, engineers are working on a variety of applications, such as more shock-resistant flight recorders, or black boxes, as well as micrometeorite-resistant spacecraft. So these are a few examples, and I would say if you go down to the chemistry level, which is the background I came from, there's an entire class of insecticides called pyrethroids that are synthetic versions of pyrethrin, which is produced by chrysanthemums. There's another entire class of insecticides called neonicotinoids that are based on nicotine. Nicotine is an insecticide in tobacco, and so neonics are synthetic versions of nicotine. And many pharmaceuticals have been developed, again, based on the study of plant extracts. And actually, I have a niece who's studying marine organisms and looking for medicinal opportunities based on chemicals that can be extracted from marine organisms. So these are all examples of teleology. What again does Romans say? For the truth about God is known to them instinctively. God has put this knowledge in their hearts. For from the time the world was created, people have seen the earth and sky and all that God made. They can clearly see his invisible qualities, his eternal power, and his divine nature. So they have no excuse whatsoever for not knowing God. So going back to that early quote that the earth is not special, God says people have no excuse for coming to the conclusion that the earth is not special. He's left plenty of evidence to the contrary. Okay, so this wraps up tonight's session, and next week we will be looking at irreducible complexity and perhaps abiogenesis. So thank you.